up Roger, Squawk 1200, radio services terminated. Fix change to White Unicom 135.0 approved. Good day.
Good night, Roger. You can proceed to the runway.
In the late 1950s, the United States Air Force began constructing ideas for a reusable glider to conduct operations for reconnaissance, satellite attacks, and air-to-ground weapons. The first idea to leave the drawing board and become a reality was Project Dyna-Soar, a collaborative research between the United States Air Force and NASA. The X20 Dinosaur was a partially reusable glider spaceplane, but this concept ended up failing due to the prioritization of Project Gemini. But what followed the failure was quite remarkable. During the 1950s, the United States Air Force began a research operation into the feasibility of a piloted glider used to perform military operations that could also be reusable. In the late 1950s, the Air Force began the development of the X20 Dinosaur. This was a collaborative project between NASA and the Air Force. In 1961, the research team began the training of 6 pilots. From this project would come groundbreaking research pertaining to fuselages that produce lift on their own, instead of from wings. Also in the 1950s, this research would be used in the development of the following aircraft prototypes: M2F1, M2F2, M2F3, HL-10, X-24A, and the X-24B. The aerodynamic characteristics tested in these trials would later be used in the design of the Space Shuttle and its capability to land from high altitudes and speeds with no external power. In September of 1966, NASA and the Air Force released a collaborative study concluding that a new space vehicle will be required to meet their respective needs in the future, and that a partially reusable systemic approach would be the most effective in terms of cost. George Muller, the head of the Manned Space Flight Office at NASA, announced a plan for a reusable space shuttle on August 10th of 1968. NASA then issued a request proposal for the Integrated Launch and Reentry Vehicle, or ILRV, which would later be recognized as a space shuttle. Instead of awarding contracts based on earlier proposals, NASA announced a staggered approach for the space shuttle program's contracting and development. The first phase, or Phase A, was a request for studies that were completed by contending aerospace companies. Next, a competition between 2 contractors for a specific component of the program made up Phase B. Phase C then included the designing process for the factors of the compounds for the spacecraft. And finally, Phase D began the production of the spacecraft. In December 1968, the Space Shuttle Task Force was created by NASA to help determine the most ideal design for a reusable spacecraft. NASA then issued contracts for study to General Dynamics, Lockheed, McDonnell Douglas, and North American Rockwell. In July 1969, the Space Shuttle Task Force distributed a report that concluded the shuttle would support a space station through launch and service missions. It would have the ability to retrieve satellites and support crewed missions for a short span of time. The report also developed the 3 classes for a future reusable shuttle. Class 1 would use a reusable orbiter mounted on expendable boosters. Class 2 would use multiple expendable rocket engines in a single propellant tank. And finally, Class 3 would have both a reusable booster and a reusable orbiter. The Space Shuttle Task Force, under the leadership of Vice President Spiro Agnew, in September 1969 issued a report requesting for the development of a space shuttle to bring people and cargo to low Earth orbit, also known as LEO, and a space tug to transfer items between orbits and the Moon, and a reusable nuclear stage for travel into deep space. After the release of the report from the Space Shuttle Task Force, a majority of aerospace engineers favored the Class 3 shuttle idea, primarily because the fully reusable design was thought to have immense savings when it came to the overall budget. Max Faze, a NASA engineer who contributed greatly in the work pertaining to the Mercury capsule, recently received a patent for his design for a fully recoverable 2-stage system that would include a straight-winged orbiter that would be mounted on a larger straight-wing booster. The Air Force Flight Dynamics Laboratory had some disagreements on the fact that a straight-wing design would be unable to withstand the extreme thermal and aerodynamic stresses during re-entry into Earth's atmosphere, and that it would not be able to provide the required cross-range capability. Additionally, the Air Force needed a larger payload capacity than in Phase A's design allowed for. In January of 1971, leadership from NASA and the Air Force concluded that a reusable delta-wing orbiter that was mounted on an expendable propellant tank would be the optimal design for the future of the space shuttle. After establishing the requirements for a reusable heavy-lift spacecraft, the Air Force and NASA began determining the design requirements of their respective services. The Air Force had expectations for the Space Shuttle to launch large satellites and had demands that it be capable of lifting 29,000 kilograms, or 65,000 pounds, to an eastward of low Earth orbit, or 18,000 kilograms, or 40,000 pounds, to polar orbit. The designs for satellites also required the Space Shuttle to have a 4.6 by 18 meter payload bay. NASA evaluated both the F1 and J2 engines that were used in the Saturn rockets, but determined that they were insufficient for the standards for the Space Shuttle. In July 1971, NASA issued a contract to Rocketdyne to begin development on the RS-25 engine that would later be used on all the Space Shuttle models, and now more recently used on the Space Launch System, or SLS, for missions into deep space. Following the selection of the RS-25 engines for the Space Shuttle, NASA reviewed 29 potential designs, and determined that a design with the inclusion of 2 side boosters should be used, and that the boosters should be reusable to reduce costs for the missions. NASA and the Air Force elected to use solid propellant boosters because of their lower cost profile and the effectiveness of refurbishing them for reuse after their impact into the ocean. In January 1972, U.S. President Richard Nixon approved the Space Shuttle, and NASA then decided on its final design in March. That August, NASA awarded the contract to construct the orbiter to North American Rockwell, the contract for the solid rocket booster to Morton Thiokol, and the external tank contract to Martin Marietta, which would later merge with Lockheed to form Lockheed Martin in March 1995. On June 4, 1974, Rockwell began the construction of the first orbiter, OV-101, which would later be entitled Enterprise. Enterprise was originally designed as a test vehicle that could be launched from a Boeing 747 to perform atmospheric testing. OV-101 did not include heat shielding or engines. Construction was completed on September 17, 1976, and Enterprise was moved to Edwards Air Force Base to begin its testing. Rockwell constructed the Main Propulsion Test Article, or MPTA-98, which was the structural truss mounted to the ET, with 3 of the RS-25 engines attached. MPTA-98 was tested at the National Space Technology Laboratory to ensure that the engines could run safely during the launch profile. Rockwell then conducted thermal and mechanical stress tests on the designated structural test article, or STA-099. This was determined the effects of aerodynamic and thermal stress factors both during launch and re-entry. Although the program had been running smoothly up until now, the development of the RS-25 uses the Space Shuttle main engine was delayed for 9 months because of the challenge issued by Pratt & Whitney to dispute the contract being earned by Rocketdyne. After much delay, the first RS-25 engine was completed in March of 1975. During engine testing, the RS-25 experienced many nozzle failures, as well as broken turbine blades. Despite these problems during testing, NASA proceeded with their order of 9 RS-25 engines that were needed for its first 3 orbiters under construction. NASA experienced significant delays in the development of the Space Shuttle's thermal protection system. Previously, NASA spacecraft used ablative heat shields to protect technology and the crew from external heat factors during launch and re-entry, but these could not be reused. Thus, NASA chose to use ceramic tiles for thermal protection of the shuttle. The usage of an aluminum fuselage in the ceramic tiles would make the heat shield most reusable, as the tiles could be replaced as needed. Construction of the Columbia Space Shuttle began on March 27th of 1975, and it was delivered to the Kennedy Space Center on March 25th of 1979. At the time of its arrival at the Kennedy Space Center, Columbia still required 6,000 of its ceramic tiles to be installed. During the second installation, it was discovered that many of the original tiles required replacement. This required another 2 years of installation before Columbia would be airworthy. On January 5, 1979, NASA commissioned a second orbiter. Later that month, Rockwell began the conversion of STA-099 to OV-099, which would later be named Challenger, which would suffer from a catastrophic failure during its launch on April 4, 1983. On January 29, 1979, NASA placed an order for 2 additional orbiters, OV-103 and OV-104, which would later be named Discovery and Atlantis. Construction of OV-105, later entitled Endeavour, began in February 1982, but NASA paused its construction due to the decision to limit the Space Shuttle fleet to 4 orbiters in 1983. However, after the loss of Challenger, NASA resumed production of Endeavour in September 1987. After its arrival at Edwards Air Force Base, Enterprise underwent flight testing with the Boeing 747 shuttle carrier that had been modified to carry the orbiter. In February 1977, Enterprise began approach and landing tests and underwent captive flights, where it remained attached to the shuttle carrier aircraft for the duration of the flight. On August 12 of 1977, the Enterprise Space Shuttle conducted its first glide test, where it was detached from the shuttle carrier aircraft and landed at Edwards Air Force Base. The original test model, known as Enterprise, completed 4 additional flights. Afterwards, it was moved to the Marshall Space Flight Center on March 13, 1978. Space Shuttle Enterprise underwent numerous shake tests and the mated vertical ground vibration test, where it was attached to an external tank and solid rocket boosters, and then underwent vibrations to simulate the stresses of launch. In April 1979, Enterprise was taken to the Kennedy Space Center, where it was attached to an external tank and solid rocket boosters, and moved to LC-39. Once installed at the launch pad, the Enterprise was used to verify the proper positioning of the launch complex hardware. Enterprise was then taken back to California in August 1979, and was later used in the development of the SLC-6 at Vandenberg Air Force Base in 1984. On November 24, 1980, Columbia was attached with the external tank and solid rocket boosters, and was then moved to LC-39 on December 29. The first Space Shuttle mission, STS-1, would be used the very first time NASA performed a crewed first flight of a spacecraft. On April 12, 1981, the Space Shuttle launched for the first time and was piloted by John Young and Robert Crippen. During their 2-day mission, Young and Crippen tested equipment on board the shuttle and discovered several of the ceramic tiles had fallen off the top side of Columbia. NASA coordinated with the Air Force to use American satellites to take images of the underside of Columbia and determined there was no structural damage. Columbia re-entered Earth's atmosphere and landed at Edwards Air Force Base on April 14th. NASA conducted 3 additional test flights with Columbia in 1981 and 1982. On July 4, 1982, STS-4, flown by pilots Ken Mattingly and Henry Hartsfield, landed on a concrete runway at Edwards Air Force Base, where President Ronald Reagan and his wife Nancy met the crew and delivered a speech. After STS-4, NASA declared the Space Shuttle operational. Years later, concluding the end of the Space Shuttle program with 5 constructed orbiters and 135 missions with 133 successful returns, the Space Shuttle was used to deploy scientific innovation among the stars, including satellites, the International Space Station, Skylab, and Mir. From its first flight on April 12, 1981, to its final landing on July 21, 2011, the Space Shuttle was the only carrier of the United States astronauts until the recent usage of the SpaceX Dragon capsule on May 30th of 2020. The overall Space Shuttle program was estimated to cost $221 billion as of 2012. Although the Space Shuttle may no longer soar in the skies today, its legacy will always remain among the great stories of American aviation history. If you liked today's video, our channel would really appreciate it if you hit the thumbs up button and subscribe to help with our growth. If you want to stay updated, turn on post notifications to see all that Forward Aviation has to offer. If you want to follow us on other platforms, follow our Twitter and Instagram using our listed handles on the screen below. If you want to join the Forward Aviation community to discuss video concepts or place additional feedback, join the Forward Aviation Discord, channel link below. Thank you very much for tuning into today's video. We hope you fly with us again soon on Forward Aviation.